Hello, welcome to the DSS Asia conference. I hope you enjoyed this conference. In this session, we will do some deep dive into the Yugabyte architecture. My goal is to compare it with traditional databases. I'm developer advocate at Yugabyte. I have a lot of questions about how YugabyteDB compares to traditional databases, to Oracle, to Postgres. I have also some good experience on those traditional databases. So I think I can do a fair technical comparison with them to answer those questions. So basically, in traditional databases, we have the commercial ones, we have the open source one with pros and cons for all of them. Open source databases like Postgres, they have many features. They are extensible. You have a lot of extensions. You have, because it's open source, the freedom. You have no vendor locking. You can move to another database, another managed service, and you have very good support from the community. So that's about the open source. I mentioned also RocksDB because we will see that we use a part of RocksDB, but we use a lot of Postgres. This is how it compares. But if you look at open source databases in enterprises, there are some things that are missing that you have to work around, that to do differently or to do with other tools. For example, if you look at commercial databases, you have transparent encryption where you can encrypt the files so that anyone who connects to the server cannot see your data. You have high availability, and that goes further than just being able to fail over. You need high availability. For example, when you have a maintenance window, you don't want to stop the application. And when there is just a network failure, you just want the database to be resilient. In commercial databases, because it was pushed by the requirements of enterprises, you have a good performance predictability, incremental backups, resource management, all those features that you do not find directly in Postgres. And we will see that for enterprises, we need to have them, and we have them in Yugabyte. So basically, the idea of YugabyteDB is to build on open source databases like Postgres or RocksDB and add the features that are needed in enterprise for critical application, critical production, like those that I mentioned. The most important is resilience, high availability. And basically, we build a database that has the same API as open source database, same API as Postgres, but with a very different architecture to be able to have all those features in a distributed way. So architecture diagram, let's start with Postgres. When you connect to Postgres, you connect to the query layer that will parse your query with the SQL text, build the execution plan, and execute it. And then the execution reads and writes to the local shared buffer in local memory and then to files on the local disk. So this works well, but as a single node, if that node is down, the application is stopped. The idea of distributed SQL is to be able to run something similar, but on multiple nodes, where if one is down, everything continues on the others. So basically, with Yugabyte, you have the same Postgres query layer deployed on many nodes. And they do the parsing, the analyze, the plan, the execution plan that is ready to execute. But when it comes to something stateful, reading and writing data, then it communicates with the other nodes and with the other layer, that is the storage. That is completely different from Postgres. In Postgres, we have heap tables and B-tree indexes. In Yugabyte, we store differently, we replicate differently, and this is what we will see in this session. Basically, we're using the query layer from Postgres and adding a spanner-like architecture to distribute the storage and the transaction. Of course, transaction to be fully ACID and having all SQL features. So let's look at it as the application that connects to Yugabyte. When you connect to Yugabyte, you can connect with any Postgres client because you connect to a Postgres backend, basically. And if you look at the version, you have the version of Postgres compatibility, currently 11. This year, we will move to 15 and then follow the versions, and the version of Yugabyte. It is a fork of Postgres you are connecting to. A fork because it cannot run as an extension. There are too many changes to make it distributed aware, but all the features coming from the fork of the Postgres code. So best of both worlds. From Postgres, we have all the drivers, the tools, the framework that exists in the Postgres ecosystem. But if you compare to Oracle, we have the possibility to connect to multiple nodes. That's not possible with Postgres. And you can compare that with RAC in Oracle, where you have multiple active nodes in a cluster. And with Yugabyte, we have this Postgres endpoint open on all nodes. You can connect on any node, and you have a Postgres backend there. Then what happens when you are connected? And here I show a variable that arrived in the latest version with the connection manager. And I look at an endpoint in a server that shows me the active logical connection and the active physical connection. And you can see that I have some connections that are queued, logical connections that are queued to use physical connection. What does it mean? It means that we have a connection pool within the database. So if we compare with Postgres, you have always one process per connection. And when you have too many connections, you use too many processes and too much memory. And then you need to have a connection pool on the application side, which works well, except when you go to microservices, and then you have multiple instances of this application side, and multiple connection pool will still connect too many connections to Postgres. With Oracle, you have, in this case, the database resident connection pool, the RCP, that runs in the database. And in Yugabyte, we have something similar using Odyssey, which is a connection pool for Postgres, but we have plugged it within the database. It is multi-threaded, it handles the connections, and the goal is that it is transparent, which means that if you do something that requires a state for your session, then it will put some stickiness information so that you always get the same connection. But if you do not use such feature that must be within the same connection, then you can use different logical connection for your calls. So when we are connected, then we have some SQL statements that are passed and executed. In this example, I just run pgbench because I can, because it's Postgres compatible. It creates some tables, and I just doing a select on one of those tables with an explain analyze. This is how you get the execution plan from Postgres. This works the same on Yugabyte. I can see that this is doing a sequential scan on this table, and you have planning time and execution plan. So planning time means that the Postgres backend I'm connected to will parse the query and build the execution plan, the optimal access to the data. When you compare, so this is exactly how Postgres works. The difference is that here, each node can do the same. In Oracle, you have a shared library cache. The execution plan will be shared by all sessions, not in Postgres and not in Yugabyte, because to distribute, we don't want a single point where all sessions have to lock and latch some memory structure. So we do like Postgres in all nodes, we parse. And the catalog is shared by all sessions in the YB master server. And this catalog has all the metadata of the dictionary. It is read at the first parse. This is why the planning time can take a few milliseconds, but then if you do a second parse, you will not have to reach out to the catalog again because everything is cached on the server. So more detail on the planning time. Here is the planning time, 8 milliseconds. And if we run the same statement again, the planning time is much lower because it doesn't have to read again from the catalog, except if some DDL has changed the structure of the tables. Then about the execution. So here to show the execution step, I'm adding a new dist option to explain analyze. In Postgres, you use buffers when you want to see the reads and writes because Postgres writes and reads to buffers in the shared buffer pool. Here, because we are distributed, we cannot read and write to local memory only. We have to talk to the other nodes. And this goes through read and write requests behind the statement. Of course, when those read requests are sent to other nodes, it adds some latency. For example, if you are in an AWS region between availability zones, you have 1 millisecond. So all the optimization that is made in Yugabyte is to try to batch as much as possible those read requests. You see here that, for example, I'm reading 100,000 rows, but I have only 99 read requests because they were batched to read 1,000 rows for each call to the other node, which makes it quite fast with good performance because you pay the latency only one every 1,000 rows. So when you compare Postgres writes to local buffers, there are some forks of Postgres which try to distribute to multiple availability zones using a remote storage like Aurora, AlloyDB, Neon. So they send the writes to storage servers. If you compare with Oracle, for example, if you run Oracle on Exadata, you can also see some remote calls to storage servers in Exadata for very specific queries, those that do not use the buffer cache. And in Yugabyte, all the reads and writes are sent to the distributed storage with batched read request, write request that are distributed to all nodes. We will see more detail about the protocol when sending those requests to other nodes. So the reads and writes are distributed, which means that if I run the benchmark itself, pgbench, and if I look at all the nodes in my cluster, here I have deployed a cluster on 3 availability zones, and I have 1, 2, 3 nodes per zone. And you can see that the reads and writes are very similar on all nodes because even if I'm connected to the same Postgres backend, the reads and writes are distributed. Here, because I have 100 of clients and I connect through an HA proxy, I have also distributed the connections, and then each connection distributes the read and write requests. So how is this distributed? The idea is that each table and each index is sharded, kind of partitioning, but automatic on the key, on the primary key for the table, on the indexed column for the indexes. In this example, if I look at the properties of my table, I can see that I have 3 tablets. This means that, and also it is sharded on hash. That's a choice. This means that when I insert a new row in the table, a hash value will be calculated on the primary key, and I have 3 ranges of hash value, and depending on my hash value, it will go to one or the other tablet. And the tablets are distributed to multiple nodes. Quickly, if I look at one table with 3 tablets, so you go into one tablet depending on your primary key, you can see that there is a range because the hash value goes from 0 to 65,535. Hexadecimal is easier, 0xFFFF. And for this range, we have distribution and replication. So the rows which are hashed in this range, go to the leader node, and the writes are also replicated to the follower node with the raft protocol. So this is our first, everything is distributed. 2 sessions reading different rows will send the reads to different nodes. And if they write, the write will also be replicated to another availability zone, so that if one zone fails, the others can just continue. This can go to multiple zones or multiple regions or even multiple clouds or some cloud providers and on-premises. Looking at more detail about that, here I'm just looking at 2 internal values in hexadecimal that we'll see later in the protocol. The first one is the table ID in hexadecimal. This is how tables are identified, tables and indexes. And the other one is the primary key that I have. I apply the hash code to get this value that will go in the different range to go to different tablets. So each row belongs to one table, and that table has multiple tablets, and the row will go to one of them. And then we can go a bit deeper on what is happening by setting a debug mode, that's for lab, not production, that will show all those read requests that are sent from the query layer, from the Postgres backend to the distributed storage. And I run pgbench again, and I look at the log, and just taking an example of it, a select for a single row was translated by the query layer to a read request coming from Postgres, because we have multiple APIs. I'm talking about the Postgres one here. And you see some information, the table ID that we have seen before. And the binary value contains the hash value of the primary key and the primary key value. This read request has a lot more information because there are some things that are pushed down. So you can see a lot more information, and I even removed them to fit in the slide. Basically, what is important is that you have this translation to read and write operations, and they are batched and flushed to be able to be sent without paying the latency for each operation. When you compare in Postgres and in Oracle, the same process, the process where you are connected to, this process will do everything, will write directly to the blocks in the block buffer, and that can be read from the disk, and that can be written to the disk. A single process is doing everything. This is monolithic. In Yugabyte, you have those 2 layers and the query layer that is stateless, which make it easy to run on many servers. It's transforming the complex SQL queries and transactions to read and write operation, all with a key. It's kind of a key value, a key document, the primary key in this case, and more information about what we want to read, what we want to write. And this is sent as a protobuf. This document is, of course, compressed and optimized to be sent to other nodes. When you write, so let's take an example, doing the same, but now with an option in pgbench that writes, does some updates and inserts. And if I look at the log after setting this debug mode to trace all requests, I can see a write operation that is buffered. You may have multiple write operations that are buffered and flushed only after many ones. And you see the values that go to the storage. So again, Postgres, Oracle, you are connected to a single process where the writes regenerate a redo log record or a while record, then apply it to the buffer, and the same session is doing that. Here we have this intermediate structure, a key value structure between the query layer and the storage that will store it and distribute it. The document that is sent here is sent to the Raft leader, and the Raft leader will forward it to the Raft followers for replication. So everything at the same level, at this key value document level. And in the execution plan, we can have more information about that. In addition to dist, I use debug, and there I have more information about what is behind that. After sending the write request or the read request, what happens in behind? Where is it stored? And you can have a clue here that each tablet is stored in RocksDB or something based on RocksDB. So very different. Postgres, Oracle stores rows in blocks, in extents, for heap tables, for B-tree indexes. In Yugabyte, we store all those key value information, so the primary key and the column value, or the index key and the other index columns in the index. We store that in a LSM tree. The big advantage of the LSM tree, but I will come back to that later, is that it's happened only, and then in background, it will be put at the right place. We can look at this LSM tree, at this RocksDB. If we go to a server, we have a RocksDB subdirectory with the table identification that we have seen and the tablet identification, and we can run a SST dump on that. Because the first level of LSM tree is in memory, but then it is flushed to SST files. And we can look at those SST files, and we will see nearly the same document with the hash value, with the value of the key, and then the other column values. And one thing that is additional, we have the hybrid timestamp. This is the clock of the whole cluster, and it is based on physical time plus a logical time. Very different from Postgres and Oracle, which store in other kind of structures like B-tree, and using SCN in Oracle or LSN in Postgres, having transaction ID. In Yugabyte, everything is versioned with the timestamp. Now, let's compare quickly the structure. The LSM tree, as I mentioned, the writes go to the first level. It's a memory table, which means that it is fast. A new value is a new version for a row or for a column, and goes only into memory, of course, protected by write-ahead logging. And then when it is full, it is flushed to a SST file, but the writes can continue on another memory table. And the SST files, at some point you have many SST files, and they are compacted to maybe bigger, but a smaller number of SST files. And when it reads from the LSM tree, what RocksDB does is merging from multiple SST files. Each of them are sorted same in memory table, and then it can read from all of them, kind of a merge happen, like In Postgres, when you do a unional with a sort, it can merge without having to resorting everything. Big advantage, when you create an index, you don't have like B-trees to read all the table and sort it to insert the B-tree. Here, you can just happen and the SST file compaction will put everything in place. It's also a structure that is very efficient for SSDs. In SSDs, you can do random reads quite fast. And this is why it's not a problem to read from multiple SSD files. The problem in SSD is more the random writes. And with this first level, where you happen only, and then you have only flushes and compactions, then you transform the random writes to sequential writes, which are much more efficient on SSD. And big advantage also, because SSD files are immutable, it's very easy to do incremental backups, snapshots, because you just take the files. The blocks will not change later. Compared with B-trees, the writes are very complex because they have to find the right place, maybe split some blocks, and I'm going fast on all that, but the creation of an index in B-tree takes time, takes memory and temporary space. B-trees are very efficient when you have a large shared buffer pool, but when you distribute, you cannot distribute the memory. So yeah, also a B-tree rewrites a lot in the same blocks. When you don't do that, when you have immutable files, then you reduce a lot the possibility of block corruptions. Of course, we didn't use RocksDB as is. It's a very adaptable key value data store. And for example, we use only the first level, the level 0. In RocksDB, for large databases, there are multiple levels. Here, we don't need it because we have sharding on top of it. And then each tablet can stay in 10 gigabytes, 100 gigabytes, with no need for higher level to manage. And other advantages, because of this iterator that can read from multiple files or mem table, we even read from 2 LSM trees, because when we have complex transactions, all the provisional records are written to a first intense DB LSM tree, and then in the background, when it is committed, it goes to the regular DB. And when we read, we can read both. When we read from the intense DB, of course, we have to check the status of the transaction to see if it is committed or not. And the wall, we don't use the RocksDB wall. We have wall at higher level, at this level between the query layer and the storage layer, the same that is replicated, the same that is used for change data capture, the same that is used for asynchronous replication. Everything is at this key value level. Of course, there are a lot of optimization added to RocksDB, especially for reads in a SQL database. We read a lot, and there are a lot of optimization done there. And if we compare quickly, with this 2-layer architecture, we don't have one single process doing everything. We have this intermediate key value API that works really, really well. And then everything is built in, not adding a layer on top of it for logical replication, change data capture, everything is within it. I mentioned it quickly, the multi-version concurrency control. We don't have the same problem as Oracle, very long rollback. If you have very long transactions, we don't have the same problem as Postgres, all those vacuum problems. In Yugabyte, all the index entries and table rows are versioned with timestamp, so no transaction wraparound problems, for example. So this is going from the application connecting to Yugabyte into the detail of storage and replication compared to Oracle of Postgres, you can see that from the application point of view, from the user point of view, it is very similar to Postgres. When you go into the detail, it is very different because it is distributed and resilient. Thank you very much, and enjoy the conference.